Think of a cat. There it is, a cat. You didn't see one. You read 3 letters and a picture appeared in your mind instantly with no effort at all. Now, the strange part, we've built machines that do the same thing. You type a cat next to an apple and out comes a picture no one has ever taken. So how does a word turn into a picture in your head and now inside a machine? To answer that, we have to answer the bigger question hiding behind all of AI. How does a machine learn anything at all? So let's take apart the simplest system that still reveals the trick. Because underneath every one of these machines are just a few ideas. And once you see them, you can't unsee them. You do this without even thinking. Read peanut butter and your mind has already supplied jelly. The sky is blue. You finish the sentence before it ends. But you don't weigh every word the same. In I grew up in France, so I speak. It's the word France, far back in the sentence, that decides the answer is French. You zero in on the words that matter. That focusing has a name, attention. Answering a question is the very same trick. How are you? I am fine. One predicted word at a time, each guided by the question. So how does just guess the next word become answering, reasoning, a whole conversation? That's the trick we're about to take apart. Here's a question and its answer, laid out word by word. How are you? And I am fine. First, embedding. Each word is turned into a small list of numbers. Here, 3 of them, a token vector. And each of those tokens is really a point in space, a direction, a vector. Let's lift all 6 out of the table and plot them, one at a time, as the space turns. These token vectors are the raw material. Now they feed the heart of attention, the query, key, and value projections. 3 small projections, query, key, and value. Each is just a little learned network. Here's the key idea. The answer's words feed the queries, while the question's words feed both the keys and the values. Each projection turns its words into a stack of token vectors, queries, keys, and values. Queries and keys meet in the attention grid, every answer word scoring how much it should attend to every question word. Weight the values by those scores, and out comes the output, one refined vector for each answer word. Now strip away the machinery and watch just those query and key vectors back in space. Keys from the question in amber, queries from the answer in teal. And a graph tracking the training loss. Now train the network, watch the loss fall, and as it does, the query I swings around until it lines up almost exactly with the key U. U now aligns with I, the most probable next word. That alignment is the machine deciding what to say next. That's attention. You're scanning a crowd looking for one friend, and there they are. You spot them in an instant. But you didn't do it by memorizing their exact face. You spotted what makes them different from everyone around them. That same versus different instinct is one of the most powerful ways to learn anything. And you can teach a machine the very same trick. Take a photo of a cat and the words, a tabby cat. To us, those are obviously the same thing. But a computer never sees a cat. It only ever sees numbers. The picture becomes a grid of color values. The words become a list of index numbers. A grid of color numbers on one side, a list of word numbers on the other. Nothing about them looks alike. So how could a machine ever learn that these two mean the same thing? To encode an image, start with the picture itself. Here, our cat. Chop it into an 8x8 grid, 64 little patches. Turn each patch into a feature vector, a short list of numbers describing what's in it. Together, they form the first feature map. Then hand that off to the encoder to downsample and then apply self-attention. On the image side, we pick up from that first feature map, the 8x8 patchified image. Slide a filter across and step it down to 4x4. Fewer positions, but more channels, more meaning packed into each. Downsample once more to a 2x2 map with 3 channels. Flatten those 4 positions into 4 patch tokens, each a 3-number vector. Add a positional embedding so each token remembers which patch it came from. Then self-attention. Every token projects a query, a key, and a value. Score them 4 by 4, soften into weights, and mix the values together. Finally, average the 4 token vectors into one. That single vector is the encoded image, the very same size as the encoded text. On the text side, the caption, "A tabby cat," is first broken into tokens, including special markers for padding and end of text. Each token becomes a small 3-number vector, its embedding. Then the same self-attention we've seen before. Every token casts a query, a key, and a value. They score against one another, 5 by 5, soften into weights, and mix the values together. Finally, take just the end of text tokens vector and project it. That's the encoded text, one 3-dimensional vector, the exact same size as the encoded image, so the two can be compared. Now the two towers meet. Here are the encoded vectors, 4 images in teal, 4 captions in blue, each just a point in one shared space. Plot them in space, and at first the cat image and its caption point in completely different directions. Take every image against every caption and measure their cosine similarity, an n by n grid of scores. We want the diagonal, every image with its own caption. The cat cell is image 1 with a tabby cat. Everything off the diagonal is a mismatch. And here's the loss we minimize. Now train. Pull each image toward its own caption and push it away from all the others. Watch the vectors swing into line and the diagonal of the matrix light up bright. The cat image and a tabby cat now point the very same way, matched on the diagonal. That's contrastive learning, the machine teaching itself that a picture and its words mean the same thing. Step back, and CLIP is really just 2 encoders that share one space. The cat image runs through the image encoder and comes out as a teal vector, and the caption runs through the text encoder and comes out as a blue vector of the very same size. Then compare the two with a single number, their cosine similarity, and that drives the CLIP loss. Matched image and caption pairs are pushed toward high similarity, mismatched pairs toward low. Do that across millions of pairs, and the two spaces line up. Someone says, draw a cat, and you could right now without even thinking about it. You know a cat the instant you see one, by its parts, the ears, the whiskers, the stripes. So picture your mind breaking a cat into those parts and setting each part down as a point in a kind of space. That's what these dots are, encoded pieces of cat, and cats naturally gather together. An apple breaks into its own parts too, that settle into their own corner. Similar-looking parts cluster together. Now, ask for a picture, and you draw from that space, visit a point, and draw whatever lives there. Ask for a cat, visit the cat region, and out of noise, a cat resolves. Ask for an apple, and you draw an apple. Drift upward toward what it knows well, and you get something realistic, a cat sitting beside an apple. Drift downward into stranger territory, and you get the impossible, a cat shaped like an apple. The same space holds it all, from the perfectly ordinary to the never seen. A machine plays this exact game. So, how does it learn that space and turn a point into pixels? Let's build it. It all starts with the image itself. First, chop it into an 8 by 8 grid of little patches, and turn each patch into a short list of numbers, a feature vector describing what's there. Now slide a small filter across that grid, blending neighbours, and step it down to 4 by 4. We lose some positions, but each survivor now summarises a bigger region. Fewer places, richer meaning. Do it once more down to a 2 by 2 map. This is the latent grid, just 4 positions left, but each one carries a lot. Unroll those 4 positions into a sequence of 4 tokens, each a little 3-number vector. Then the same trick we saw before, attention. Every token projects into 3 roles, a query, a key, and a value. Each token scores how much it should attend to every other, softens those scores into weights, and mixes the values together accordingly. And unlike a classifier, we don't average it all into one vector. We keep all four, a 2x2 map of three-dimensional latents. This is Z. One step remains. Pin each of these latents to the nearest word in a learned vocabulary. That's the quantizer, coming up next. Here's what the quantizer works with. On the left are four latents, each a row of three numbers and each also a point in space, a teal sphere. And here's the codebook, the learned vocabulary. 8 entries, each its own row of three numbers, its own amber sphere. These are the only building blocks we're allowed to use. To match latents to codes, we build a table, every latent against every code, measuring how close each pairing is. Take the first latent, compare it against all 8 codes at once, filling in its row of the table. The closest code wins, the brightest cell, and the latent snaps right onto it. Do the same for the other 3. Each latent measures itself against every code and snaps to its nearest one. Now every latent is a discrete choice, an index plus the code vector it points to. That's ZQ, 4 discrete three-dimensional vectors. To turn that vocabulary back into a picture, we start from ZQ, the quantizer's 2x2 map of code vectors. First, lay it out as a sequence of 4 tokens again, each still 3 numbers wide. Then let them attend to one another, one more time. Every token projects into a query, a key, and a value. They score how much each should listen to the others, soften those scores into weights, and mix the values together accordingly. Fold that result back into a 2x2 feature map, and let's tilt into 3 dimensions to watch it grow. Now the second leg of the U, a transposed convolution grows the map, from 2x2 up to 4x4, and again up to 8x8. Space expands, channels shrink, climbing back toward a full image. Finally, project those features into actual pixels, the reconstruction X hat. How does it learn to do this well? 3 pressures. The first, reconstruction, make X hat match the original image, pixel for pixel, and in overall feel. The second, the codebook and commitment terms, keep each latent and the code it chose close together. And the third, the clever one, an adversarial critic, a patch-GAN that judges each little patch of the image as real or fake. Add the 3 together and a single gradient, delta, flows back to train both the decoder and the codebook. And it's that adversarial push alongside reconstruction that gives sharp, believable images, instead of a cautious, blurry average. Let's watch the vocabulary itself get trained. Here's the space and the 2-term loss we're going to minimize. These dots are the latents, encoded image patches, grey for bits of cat, red for bits of apple. They fall into 2 natural clusters. And these amber spheres are the codebook entries, the very rows shown on the left. Right now they start clumped together, badly placed. Each latent snaps to its nearest code. The first term, the codebook loss, pulls each code toward the average of the latents that chose it. The second, commitment, gently pulls each latent toward its code, and already the error drops. Repeat the 2 over and over, and the codebook spreads out to cover the data, the loss falling with every round, until every cluster has code sitting right on it. A good discrete visual vocabulary, trained, not given. Now, watch all 3 work together, and the mystery comes apart. You give the words, and the vocabulary machine paints a rough guess, reusing the codebook, the decoder, and the upsampler we already built. The comparison machine looks at that guess, and your words in one shared space, and measures a single thing. How far apart are they? Then it nudges the picture to close that gap, and measures again, and nudges again. Rough guess, measure the gap, nudge toward the words, over and over. And that loop is the whole secret. That is what learning has been this entire time. Measure how wrong you are and take one small step toward right. Do it 1,000 times and a smudge of noise becomes a cat next to an apple. So, how does a word become a picture? It becomes numbers in a space. Those numbers pay attention to each other. The machine learns, by comparison, to put words and pictures in the same space. It learns a vocabulary of visual pieces, and then it paints, measures how wrong it is, and nudges, again and again, until the picture matches the words. Represent, attend, compare, remix, nudge toward the goal. That's not one trick for making cat pictures. That's more or less how all of it works. The chatbots, the voice assistants, the tools you already use. The newest systems might swap out a piece, but the ideas underneath don't change. And here's the part I can't get over. Everything you just watched, your mind did all of it in the time it took to read one word: cat. We spent this whole video building a machine to do what you did without noticing. That's the mystery, and we've only just started to solve it.